Hey guys, Miss Duncan here. We're going to be talking about exponential functions today. Before fall break, we discussed rules of exponents, so just basics, how exponents work. And today we're going to be shifting over to exponential functions. So they're very similar to linear equations or functions in that there are rules for growth, there's rules for decay, so rules for the values to go up, rules for the values to go down. And just like linear functions, they have two main parts. So linear functions have a b value that tells you the y-intercept. We also call that like the initial value. With exponential functions, this number in front, that's the a value, and it's the same idea. It's your y-intercept, it's your initial value. With linear functions, we have m, which represents the slope, and that's not supposed to say initial value, that's supposed to say growth rate. So what happens is that will grow by adding that amount. But with exponential functions, we have the base or the multiplier, and it grows by multiplying that amount. There are some basic rules. So to have growth, you would need a slope that's bigger than 0. So like 3, 4, 5. For decay, you would need a slope that's less than 0, so like negative numbers. And then where it doesn't grow or decay, where it just stays flat, would be a slope of 0. So that's linear functions. With exponential functions, to make them grow, you need a base or multiplier that's bigger than 1, so something like 2, 3, 4. For decay, that's actually decimal values. So for it to go down, it's values between 0 and 1. Now, you cannot have, there's no growth or decay if the base is 1. That actually just makes a flat line. And you can't have the base be 0 or negative. And we can get into that later. 0 would basically be it wouldn't exist. And a negative multiplier, it causes some interesting values where you don't have a graph that makes sense. Sorry, my cat's here. This is Randy, if you haven't seen him before. All right, so we're going to be trying some similar linear and exponential tables to see kind of how it's different and how we put these together. So with a linear table, the first thing I want to look for is the y-intercept. And that's this second part that doesn't have an x on it. And that always goes above 0. So I have a y-intercept of 4. That's going to go here at 0. And then a slope of 3 means that I add 3 every time I go forward. So 4 plus 3 is 7. Plus 3 is 10. Plus 3 is 13. Plus 3 is 16. Plus 3 is 19. And so on. So you're adding 3 every time you go forward. And then to go backwards, we just do the opposite. So to go backwards here, I'm going to minus 3. And so that tells me that value will be 1. So for an exponential, it's similar, but we're doing multiplication instead of addition. So here I have an initial value of 4. And then it multiplies, the base or the multiplier is 3. So I'm going to multiply by 3. 4 times 3, that makes 12. Times 3 makes 36. Grab out my calculator here. 36 times 3, so you're always multiplying by that same number, is 108. Times 3 would be 324. Ooh, that's terrible. And so on. So we're always multiplying by 3. Then to go backwards, we would do the opposite of multiplying. We would divide by 3. So I'd have 4 divided by 3, and you could actually just write that as a fraction, 4 thirds. All right, so that's how you do a table. Very similar, but we're doing multiplication and division instead of addition and subtraction. And we can see what those graphs look like. This is the 3x plus 4, and so it starts at 4 and it adds 3 every time. And then if you have 4 times 3 to the x, again, it starts at 4, and then the next value up would be 12, and then it's going to get steeper and steeper. And so it has this kind of curved effect. And we can see as we go backwards, it gets shallower and shallower. It doesn't ever actually reach 0, but it gets smaller and smaller and smaller there as you divide. So these ones are similar, but these are decay. So these ones are ones that go down instead of up. So if I have a linear function that goes down, again, this is a similar idea here. I'm starting at 4. And the slope is -3. So I would subtract 3 to go forward. So 4 minus 3 is 1. Minus 3 is -2. Minus 3 is -5. Minus 3 is -8. And so on. And so then to go backwards, I would do opposite, which is add. So for an exponential table, we're going to have a similar idea. And so this one, I have 400 as my starting value. The reason I chose a big number is because these decrease so quickly that you want to have a bigger starting number so that you can see what it looks like. And then we're multiplying by 0.3. So I take 400 and I multiply it by 0.3. So 400 times 0.3 is 120. Times 0.3 is 36. See how quickly those decreased? Times 0.3 is 10.8. Times 0.3 is 3.24. Okay, so I'm multiplying by 0.3 every time. Then to go backwards, I can divide by 0.3. And it seems weird, but that will actually make numbers go up. Dividing by a decimal makes numbers increase. So I do 400 divided by 0.3, and that gives me 1,333.33 repeating. To show that a number is repeating, you just put a line over it, and that shows that it's those same numbers over and over again. So 33 repeating. And again, we can look at the graphs for that. So here, if I start at 4 and subtract by 3, so the slope is -3, we can see that those values are going down, but it goes in a straight line. Where if I have 400 times 0.3, here it starts at 400, there at 1, you're at 120, and so on. And so it goes down, and we can see how those numbers were getting smaller and smaller and smaller, closer to 0, but they never actually reach 0. You get close, but not 100% there. Trying to go through this quickly. I always feel bad when I make a long video. So reading tables is pretty simple. Sometimes you can read it without having to do much math. So the first thing I look for is the y-intercept. This is 5. So I know that my A value is 5. And then what I need is my multiplier. I have to figure out what does it multiply by every time I go forward. Well, here it goes from 5 to 15. Well, most people know 5 times 3 makes 15. And so you can tell that pretty quickly is that it's multiplied by 3. And we can check that by trying that out on other numbers. Is 15 times 3 45? Yes. Is 45 times 3 135? Yes. And so we would say that it multiplies by 3 to go forward. So that would be the equation. We can use f of x like we did before, but I'm just trying to keep it simple with y. Now, sometimes the numbers are trickier to tell, but it's actually still pretty easy to find the equation. So we're still starting with our a value. Forgot to write that up here before. So here for our a value, we have our y-intercept is 2.8. And then what we need to find is the multiplier. So what I know is that 2.8 gets multiplied by something to make 7. So 2.8 gets multiplied by b by the b value to get you to 7. So then I can write that out as an equation and solve it. So I know 2.8 times the b value gets us to 7. So then I can divide both sides by 2.8. And I get b equals 2.5. And so then I can check that that's true by testing it out on the table. So if I check on my calculator, the next value, so if I do 7 times 2.5, I should get that 17.5. I don't know if you guys can see this on the calculator, but you do. And so that's how you can tell that it worked. Now, what you'll also see are exponential equations that have to do with rates or percents. And all that is you'd have to take a percentage and turn it into a decimal. And if it's growing by that percent, you do 1 plus. So that's like basically saying 100% plus this percent. If it's decreasing, decaying by that amount, you would do 1 minus. So 100% minus that percent. So there's some examples on here. So if I have $115 in a savings account, interest is earned at 4% per year. So you can make money in a savings account. That would be an equation to show how much money I would have after a certain amount of years. Cars depreciate in value, meaning that they have the most value when they're brand new, but every day even that they are off the lot, as they say, it decreases in value. It's not worth as much as when it was brand new, which is why you could get used cars for cheaper than new cars. And so if I get a $25,000 car, it can decrease at a rate of 22%. And so that would be an equation to represent that. I'm going to do a couple of examples, and then we'll be done with this video. Okay, so this is actually like real data here, which makes me a little sad. So polar bears, there's only 26,000 polar bears left on Earth, which really isn't that many polar bears. There's more in captivity, but that's the amount of just wild polar bears that are left. And so that would be our starting amount here. We're calling today the starting amount. So A is going to be that 26,000. And then, so that's going to be at year 0, which we're calling today. Now, they have been studying the polar bears, and the rate is probably going to change, but currently the rate is about 20% decrease every decade, every 10 years. And so we can kind of predict from there on out how many polar bears there would be. So to do 20% decreasing by 20%, first we're going to take that percent and we're going to turn it into a decimal. And so to do that, you divide by 100, or you can move the decimal place 2 places to the left. I like just dividing by 100 because then you can guarantee that you have the right amount of decimal places. So I do 20 divided by 100, and that gives me 0.2. And so in my equation, because it's decreasing by 20%, my b value, is going to be 1 minus that 20%, minus 0.2. Which means that there is 80% of the bears remaining after 10 years. So 0.8. So we're going to multiply by 0.8. We're going to see what this polar bear situation is looking like. Okay, so we're starting at 26,000 polar bears, and every 10 years, every decade, they decrease by 20%, so there's 80% remaining. So I go into my calculator, and you can do this by multiplying by 0.8, but I'll show you how to do it as a function. You know, I should probably do it in Desmos since you guys are more familiar with that, and you can see it on your screen easier. I'm just so familiar with my calculator that I prefer to use that. Oops, Desmos. I just need the scientific calculator. Okay, so 26,000 polar bears, and we're multiplying it by 0.8, so 80% left after 10 years. Move my face out of the way. So after 10 years, now there's 20,800 left. Oops, I don't know whether there. 20,800. So then if you wanted to skip ahead 50 years, 5 decades, we can actually calculate that without having to create the rest of the table. So what I can do then is I can say, clear all, I'm going to put in my equation, 26,000, parentheses, 0.8, and then the exponent will be the amount of decades I'm looking for. So I was looking for 5 decades, which is 50 years. It's 5. That gives me 8,519 with a decimal. You can't have parts of a polar bear, so we'll round that up to 8,520. So if the polar bear decrease in population continues as it is for the next 50 years. So when you guys are adults, there will only be about 8,000 polar bears left. Now that rate could increase or decrease depending on a lot of things that we do as humans. So this is another example, and this is a real example. I just bought a new laptop online because my school laptop is falling apart. So I bought it on my credit card for $415. I changed the interest rate a little bit because I have a really good interest rate, but I know that's not what everybody else has, so I changed it to something else. So we're going to look at what I would owe on that bill, and that's considering like I'm not paying anything. We're going to look at how the amount of money I owe increases if I don't pay any money at all. So I have my starting amount of money, which is the cost of the laptop that I bought on my credit card. So that's going to be year 0. I owe $415. But I have an interest rate that they charge me of 22.75%. And so my rate, I'm going to do 22.75, and I want to make that into a decimal instead of a percent. So I'm going to divide by 100. And percent, that's exactly what it means. Percent means per 100, so it means divide by 100. And that gives me 0.2275. And so for my base value, my multiplier, it's going to be 1, so 100% of the bill I owe, plus, because I'm increasing the amount I owe, by 22.75%. And so my multiplier here in the equation is 1.2275. Just add those together. And this is assuming I don't pay anything on it. And this can actually happen quite a bit because they have these offers where they'll say like no interest for 5 years. And that doesn't mean you don't ever owe that interest. It just means if you don't pay it at all in those 5 years, that it suddenly adds on after 5 years. And so a lot of people get caught in scams like that. So anytime you see like no interest for 5 years, you still have to pay it. It's just if you don't pay it off in 5 years, you owe all that interest all of a sudden. So now we're going to multiply. So 415 times 1.2275. And that gives me $509, and we're talking about money, so there's only 2 decimal places. That just rounds to 41 cents. So $509.41. And that's just 1 year. How many cents was that? 41. So that's just 1 year of me not paying anything. I already owe now an additional what is that? 509 minus 415, $94. So I already owe an additional amount of money just from not paying it and owing the bank. And then again, we can see what happens at 5 years out by just replacing that X with a 5. So if I don't pay anything on this for 5 years, which I should not do, it would be bad for myself and my credit score. Let's see how much I would owe on the computer now. So the exponent will be 5 years. All right, so now We're going to round that up to cents, so that'll be 53 cents. So $1,156.53. And so what I've done by not paying for this for 5 years, just letting it sit on my bill, minus 415, is now I owe an additional $740. And so I now owe more than the price of the computer in just interest charges. And so that's kind of one of the things about credit cards that you guys will learn about in the next few years. All right, so that was a little bit about exponential functions. The video probably took longer than I expected because they always do. I need to know when to shut up, but I'm a teacher. So here's some optional practice problems. You don't need to do these, but if you just kind of wanted to try some more things, here's some optional practice. We're also doing the Desmos activity in class this week. All right, have a lovely, lovely week, and I will see my students at least in class.